Hi everyone, welcome back to day 46 of me coding every day. Recently we've been looking at these greedy problems. Yesterday I did jump game. Today I'm going to do jump game 2. I'm going to start this episode by redoing jump game a different way. So I'm just going to comment all of this out and forget about it. So I looked at the solution and I also saw a comment on my last video about a different way to do it that kind of made more sense to me. So I don't remember the exact code, but I do remember. So for those of you just tuning in, I'll read the problem. You are given an integer array nums where each element nums of I indicates your maximum jump length at that position. Return true if you can reach the last index from starting at 0 or false otherwise. So basically each number tells you how many indices ahead you can jump. So with 1, you can jump to this index. With 2, you can either jump here or here. And then with 1, you can jump here. The question is, if I start at this point, using any combination of jumps, can I reach the last point? And if you want to see my attempt to this, you can watch yesterday's video. So what I've okay, so now the solution that I want to code is basically, okay, so we start here. We want to see, can we reach here? And then we loop through all of these and we basically keep updating where we want to reach. So for instance, if we look at this problem, we see that if we could get to this 1, then we can, get to it's true, we can return true. Because if we can get to this 1 from this point, we can just jump there. So now what we do is say, can we get to this 1? So we remake the end point to this 1. Okay, and then this 0 cannot get to 1. 2, this 2 can get to the 1. So then we move it and we say, can we get to this 2? Because if we can get to this 2, we know that we can get to the whole thing. Then our I goes to 1 and we see that 1 can get to 2. So then we move our goal to here. And if our goal, by the time we're done looping, if our goal is 0, we return true. And otherwise we return false. So for I in range, so we're going to start. So if green is the length, and this is index length minus 1, we're going to start at index length minus 2. So length of nums minus 2. We are going to continue until index -1 over here, which we don't want included, and then we're going to step by -1, which means I is going to decrease by 1 at every step. Okay, so our first thing we want to check is, can we reach our goal? So I'll say goal. Did I mute? No, I'm still good. Okay, so goal is going to start at length of nums minus 1. So our goal is going to start here. That's just the little arrow I was drawing, right? So now I is here. And we're going to check, can we reach the goal from here? So I'm guessing to do that, we want to take this value. So we want to say, like, is whatever index we're at plus the number. So here would be, let me just index these real quick, 0, 1, 2, 3, 4. So is position 3, and if we jump 1 ahead, is that greater than or equal to our goal? So of course, if this was a 10 or a 4, remember the problem, we can jump up to 4 positions, so we can do greater than or equal to, not just equal to. It doesn't have to be the exact number. So that's where this greater than or equal to comes. So I'm going to say if I plus nums. Okay, so if I plus nums of I is greater than or equal to goal, then that means this becomes our new goal. So if we can only just reach this new position, then we can solve the problem. And then I will continue incrementing. So we'll say goal equals I. And if it can't, so what do we do if it can't? If it can't, then we do nothing. So for instance, like consider the example, I don't know, 0, let's say 0, 0, 2, right, from this example. So we know if we start here, we would be able to reach here. So our goal would be 0, and then I would start here, and hey, 1 plus 0 is not greater than or equal to 2. So we don't want to return false, because just because this 0 can't reach it doesn't mean all the numbers can't reach it. So then we move I, and then 2, eventually we do get there. So I think that's all you need. And then what we're going to say is we want to return if our goal is at 0 or not. So if goal equals 0, we want to return true, otherwise return false. All right, let's see if I have any errors there. Okay, let's see, any errors? No, okay. So that's kind of a more clever way of thinking about jump game. And I remember that thought appeared in my head last time. I thought, what if we go backwards and do something like that? But I just thought of a different way of doing it, which also worked, but this way seems just more simple. Okay, so that being said, let's look at jump game 2 today. So jump game 2. I've never even opened this tab. Okay. You are given an array of integers nums, where nums of I represents the maximum length of a jump towards the right. Okay, same thing from index I. For example, if you are at nums of I, you can jump to any index I plus j, where j is less than or equal to nums of I. Okay, that's same exact thing. You are initially positioned at nums of 0, same thing. Let me see, not muted, okay. Return the minimum number of jumps to reach the last position. You may assume there is always a valid answer. Okay, so it's essentially the same exact problem, except now we're assuming that we can always reach it. We can always reach it, but we want to return the minimum number of jumps. Okay, so what if instead of just storing... Okay, so let's look at this example. 1, 2, 0, 1, 0. 1, 2, 0, 1, 0. So in here, there's actually only one case. There's only one possible combination, so this probably isn't a good... Let's look at their test cases. So we have 2, 4, 1, 1, 1, 1. Okay, this is a good example because there's many different paths. 1, 1, 1, 1. Delete this. Okay, so we have to reach the last index, right? Yes, return the minimum number. Okay. So in a typical like dynamic programming fashion with this sort of stuff, I guess you would just save the minimum number at every point and kind of work backwards. So I'll start with that. I could also start with the decision tree, but I'm just gonna, since we just did jump game 1, I'm just gonna try something similar. So here, the minimum number of jumps, so in purple is gonna be the minimum number of jumps. So here, the minimum number of jumps, or let's say the jumps required to get to the end from this point is 0, because you are already at the end, so you don't need to jump. Here is 1 jump. Here is 2 jumps. Well, let's define this as, so if we can get to this position, it's 1 plus whatever it is at that position, like I plus j or whatever. So here it's going to be 1 plus 1 equals 2. Here we can jump there, so it's going to be 1 plus 2 equals 3, like that. So it's going to be interesting when we have multiple combinations here. So 4. So this has many combinations. So 1, 2, 3, 4. So it could be 1 jump 4 spaces away, So it'd be like I plus 4, right? And then 4 would be a variable that we would decrement every time. So this would be 1. We could have 2 plus I plus 3, which is this one, which is 1. Or sorry, it would be 1 plus 1 equals 2. Then here would be 1 plus 2 equals 3. And 1 plus 3 equals 4. So if we jump here, it would be 1 plus 0 jumps to get to the end. If we jump here, that means we only need 1 more. If we jump here, it means we need 2. If we jump here, it means that we need 3. All right, so let's consider this case now. So this would be n squared, this type of thinking, where at its n positions and at every position, you do the value at that position, many calculations. And you would just take, so the answer would be you would take the minimum of these. So that would be the n squared solution. I don't know if you can do better than that or not. Okay, so then here at 2, it would be, so there's 2 places you could jump. So let's say we jump to the max. That would be 1 jump plus however many jumps it takes to get to the end at that point, which is 3. If we jump here, it would be 1 plus the minimum number of jumps it takes to get to the end from this point, which is 1. So 2. So the final answer is the minimum of these. The minimum of 2 and 4 is 2, so it should be 2. Okay, and let's do that same logic for another problem, and I would be happy coding that up. I don't know if there is a linear way to do it. I think I would be happy with an n squared though, because with these sort of dynamic programming questions, but this is a greedy question, so maybe we can use some heuristic or assumption to narrow it down to linear time. Let's try the other example. I'm definitely going to code the n squared solution, and then maybe I can... I wish there was a button that told me the time complexity, but I guess in interviews there's no such button. Okay, so same thing. Here, we can't jump anywhere. It doesn't matter, whatever this number is, it's always going to be 0. Here, 1 plus 0 equals 1. Here, now there's 2 options, so we're going to take the minimum of 1 plus 1 and 1 plus 0. That'll be my minimum notation, and that equals 1. 1 plus 1 here equals 2. Now here it's the minimum of 1 plus 2 and 1 plus 1, so 2. So this should be 2 as well. Okay. Okay, so this will almost certainly work. So I'm going to do this. What is greedy about this? I don't really know. This seems sort of like just a dynamic programming solution, but I think with the greedy problems, it means that all right, I'll just code this up, and that might be what the solution is looking for. Okay, so what do we need? We need a dynamic programming array, which is the purple. And I guess we can set it to -1 times the length of nums. Then we'll say for I in range length of nums. And we're going to go backwards again. So we'll do length -2, -1, -1 like that. So I will start here. Okay, let's imagine that I is here for... So now we want to loop 2 times. So we'll say for j in range length, no length, in range nums of I. So we're going to loop nums of I times, so 2 times, and we are going to say, or maybe we could, instead of doing this, we could just splice it. So if I say like m equals the minimum of the list, so nums, and then we splice it from I, wherever you are at I plus 1. So start at I plus 1 up until I plus nums of I. So let's just look at this case here. So we have 0, 1, 2, 3, 4. So we want to start in this case from 3, and then we want 5 to be there. So we can define 3 as I plus 1, and we can define 5 as I plus 1 plus nums of I, correct? 2 plus 3 plus 2. 2 plus 1 plus 2. Okay, so I, nums of I. Let me just make this more readable. I don't know if that's more readable. I plus nums of I plus 1. Spread out. Is that more readable or less readable? I don't know. Okay, so this will take a splice and then take the minimum of that. So we would say that dp of I equals 1 plus, so like one jump plus the minimum of that. And then we could just return dp of 0 like so. Minimum is an empty sequence. Okay, so could that be if we're at a 0, then it would be from, yeah, then it would be empty. So how do you take the minimum of an empty sequence? You can't. So if we're at a 0, what should we do? If we're at a 0, I guess we can say if nums of I does not equal 0, like that maybe, because then we'll just leave it at -1. Or should it be 0? Or like, should it be infinity? Because we never want to pick 0 as the minimum. Let me take this as a test case. Still wrong. Okay, is it an error or is it just wrong? Okay, it's just wrong. So let's look at the logic here. 2, 3, 0, 1, 4. Wait, what? How is this working? I also want to say that the last element should be 0. I don't know if that'll change anything. It didn't. 2, 3, 0, 1, 4. So I'm starting them all at infinity. My thought was if this was -1, I didn't want something to pick the -1. If that makes sense. Because it would result in a low number. Okay, so 4. Alright, so we'll start here. So nums of I. So we start here. So we need to make this 0. Let me make sure that's working. Yeah, okay, that's working. Do we need dp maybe? Is that? It's probably that. We want to go through the dp list, right? We want to look at the minimum of these. Okay, yeah, that was it. So you don't even need that? You must need that. Yeah, okay. Okay, so this is the n squared solution. And you do need this as well, right? Because if it's 0, it'll give you empty sequence. Yeah. All right. All right. So that's n squared, which normally is fine, I think, for dynamic programming solutions, and it's only of size 1000. So 1000 is, so if we look at n squared, it would be 1000 times 1000, which is 1,000,000, which is totally fine. All right. Let me, I'm going to try to submit it on LeetCode and see where my solution ranks among other ones. And then if it is really behind, then I will assume there is a linear solution. Okay. Maybe actually there is a linear solution. Let me try again. Yeah. It seems to be, there seems to be a linear solution. Okay. All right, so we're 20 minutes in, so we have some time. I don't have too much time today. Okay, so how can we do this linearly? So what assumptions can we make? Could it be that is this part just really slow? Because we have to build the list. Like, is it better to just do for j in range? All right, before I worry about that, I'll try changing that, but if I get stumped. So let's look at 2, 4, 1, 1, 1, 1. So far, all of these are infinity. Okay, so we know that this takes 0. This only has one possible combination, which is 1. This takes 2. So could we say, we can't, is there, okay, so when we get to 4, is there a heuristic on which path to take? So could we store the index of the most minimum and see if it can reach the most minimum? Like, could we, my point is, could we store everything into like a priority queue or something and then pop from that? So we'd pop here and it'd be like, okay, can you reach this position? Because this is the minimum one that we have. And if you can't, then we go next. Let me try to think of another example. I guess if we have like 0, 1, 0, 2, 0, 1, 2, 3, 2, 4. Okay, I'll try this one. Okay. So this is 0. In jump game, is there no examples that give this out of bounds? Because if we had this example, for instance, let me try it. 4, 2, 3, 1, 2. Wouldn't this give my solution an error actually because it goes out of bounds? No? Because wouldn't this say minimum of dp I plus 1 to, how is that not out of bounds? Because this should evaluate to, is it just how splicing works? Like if you go out of bounds, it doesn't give you an error? What happens if I say print nums of, let's say, so what's the length of this? 6. So if I said from index 5 to index 7, would this give me an error? No. Okay. So it looks like, I didn't know this about Python splicing, but if you go out of bounds on the splice, it doesn't give you an error. So for instance, we have no index 10. It'll just chop it off, I guess. So I didn't know that. So that's why that's not getting a problem. Okay, so then 2 is 1. 1 can only go one place, so it's 2, 1 plus 1. 3. Okay. So should we store, like, can I store, like, min index? Equals, and let me just index these. 0, 1, 2, 3, 4, 5. That our min index equals 4. And then it will just look at min index and say, okay, this is 1 plus 1. So 2. Our min index is still this. So it's basically like jump game, except we want to do the longest jumps. We want to maximize our jump distance. We want to maximize our jump distance. Right? Well, not necessarily. What if we had like 4, 0, 4, 1, 1, 1, 0. So in this case, the correct path is 1, 2. But here you might be tempted to go 1, 2, 3. You might be tempted, if we want to maximize jumps, you might be tempted to go here. Maximize jump length. You might be tempted to go there. But the reality is you should go here. So we want as few jumps as possible. So my question is here. So we see that we cannot reach index 4 with this. So then that's what I would maybe like pop from our priority queue and get the next most minimum index. And then it would say, okay, that's, and I guess I would sort them by like the closest one to the left. So I'd say, okay, that's 2. Or that, yeah, index 2, can you reach that? Then yes. But that's just a more optimized n squared. Is there any way we can just inherently know? Yes, maybe there is. Is there? Well, okay. Okay. So here, it's 0. Okay, so 2, we know we can only look within here. So the minimum index right now is 5. And we can reach that, so we just add 1. And now minimum index, well, it's still 5 technically. Actually, 5 is still the minimum index. Okay, so now we look at 1. Now 1 can only select the minimum from here. So it would be 1 plus 1. 3 can only do it from here. I feel like you kind of have to, because then like you can't really get rid of information over here, because if this was 9, then you would have to go back and use this information. Is there a way we could just look up in O of 1 where this one should jump to? If we can look up in O of 1 where this should jump to, then we'd be good. We could get linear. So we could map, if you can jump to index 5, you should, like, if you can jump up to index 5, you should jump to index 5. If you could jump up to index 4, you should jump to index 4. If you could jump up to index 3, you should jump to index 3. Okay, I think I have an idea. So in this case, okay, so we'll start. So I'm going to try doing like a dictionary thing. So we have 0, 1, 2, 3, 4, 5, 6. So here, if you could jump to index 6, you should jump to index 6. Okay, so this says, hey, I can jump to index 6, so I should do that. Now, if you can jump to index 5 only, the minimum in that is 1. So if you can only jump to index 5, you should jump to index 5. Index 4, if you could only jump to index 4, you should jump to index 4. 3. So 3, this actually might work. Okay, so then 3, if you could only jump up to index 3 so far, you should jump to index 3. Okay, and now 2. So now this is where it gets interesting. It's not exactly what I was thinking, but okay, so now 2 looks and it says, hey, I can jump to index 6. I can jump to index 6. So if you can jump, so this is now 1. So now all of these should be 2. And this should be 2 also. My point is, when we get this new information, now we know if you can jump from 2 to 5, if you're, this information tells us that maybe I shouldn't worry about a hash map yet. But when we get this information, we know, like, jump to 2 now, which might be all we need, because we can say, like, hey, this doesn't matter anymore because we found a shorter way. So then here you can jump anywhere. Here is 4. So we can say, we can use this number and be like, oh, I should just jump to 2 instead now. Okay, let me try another examples. So 0, 3, 6, 6, 5. That's 2, 2, 5. Okay. So I'm just going to try thinking about how I would do it algorithmically. All right, so 0. So like the place to jump to right now. So obviously though, like if we could just jump to the end, so it's almost like 2 became the new goal. But it's like how... So this was the new goal until this was the new goal. So basically this overwrote these 2 only. So I could do it in n squared, obviously, where if you get this, you can check, like, okay, so this became the new goal. All right, so let's try moving the goal again. So here is the goal. 3 can make it. So here's the goal. 6... Well, so we can't really move the goal because 6 can get right to 0, which is actually more, that's advantageous than 3, because this can do it in 1 jump, this can do it in 1 jump, this can do it in 1 jump. So with 2, it doesn't matter which one you pick. So this can do it in 2, but I had to do n operations here. Then 2, this can do it in 2, but I had to do n operations here. And 5. Maybe we store the furthest point to the right or to the left that is useful to us. Like this 6 is useful to us because these actually don't matter anymore. I think that's important. These 2 don't matter anymore. Once we encounter a 6 with 1, so would we... Okay, so it's like 0. So 0 jumps. So the furthest index to the left, which you can obtain the solution at 0 jumps, is index 6. Then we go here and we say, hey, this is 1 jump, and that's the furthest 1 jump we've encountered. So we say the furthest 1 jump that we've encountered so far is index 5. And then we say, hey, but 6 is also 1 jump. And how did we get that? We looked at the 0 jumps. So we look at the 0 jump. This is like the same thing as a priority queue, I feel like. All right. This might be faster though. Okay, so this, we say, hey, we can actually reach index 6 from here. So that means it's in 1 jump. So we can update this to index 4. Okay, and now this will check, can I reach the end from here? Yes, I can. So, and that's in one jump. So now I can update this to index 3. Now 2 says, can I reach index 6 from here? The answer is no. Okay, so can I reach index 3 from here? And the answer is yes. The answer is yes. So then we add 2 jumps is index 2. And then this 2 says, can I reach index 6 from here? The answer is no. So can I reach index 3 from here? The answer is yes. So now this becomes the furthest thing to the right with 2 jumps is index 1. Then 5 says, can I reach index 6 from here? And the answer is no. Can I reach index 3 from here? The answer is yes. So 5 is the newest one with, so index 0 is the newest one with 2 jumps. So my only problem with that is it's still kind of n squared though. It's still kind of n squared. The only thing is, instead of looking at just the minimum of all of them, it does save a lot of repetitive work because you just check this. Okay, so I'll code this. I don't know, because for instance, you need this information because if you introduce another number, let's say 10 at the end here, right? Like if you have a 10 here, you do have to check, hey, can I just reach the end from here? You know, and yes, you can. So then the minimum number of jumps would be actually, you'd update this to 1. You know what I mean? And then like so instead of goals, it's like, instead of just setting the goalpost, it's like the goalpost for each number of jumps. So like if Brown, so here is the goalpost for 0 jumps, which you check first. Here is the goalpost for 1 jump, which you check second. And here, you know, at the time, here was the goalpost for 2 jumps. So we say like, hey, can we shoot to this one? No. What about this one? Yes. So then, because this is 2 and its index is less than the index of the previous 2 goalposts, we move the 2 goalposts to this. So instead of searching, nums of I times, you're searching this many times, like the number of goalposts that you have so far, which seems like it would be a lot shorter. Even in the case of all ones, 1, 1, 1, 1, 1, 1. So this would be the goalpost of 0. This would be the goalpost of 1. So this is like the worst case where it's still n squared, because this number has to check, can I reach 0? No. Well, maybe we could we use some heuristic? Can we do this in O of 1? So instead of checking, can I reach 6? Can I check what's the nearest element? What's, like, if you were to put me in this list, what's the next lowest one? And that would be binary search, actually. You could do that in log n time. So, for instance, here, 1 plus 2 is 3. So we would scan our list and say, So we would binary search it and be like, hey, the next lowest thing. All right, let me try it with that. Let me try it with that binary search idea. Okay. So if this works, then the solution would be n log n. I'm not sure if it will, though. Okay, so you'd start here with 0. So this means that for 0 jumps, the furthest index to the left to achieve the solution in 0 jumps is index 7. So I don't know if we should have it like 7 maps to 0 or whatever, but let's say number of jumps, then index, like leftmost index. So in other words, this is the leftmost index. Okay, so given number of jumps, this maps to the leftmost index that can achieve the solution in that number of jumps. So far, the leftmost index that can achieve the solution in 0 jumps is index 7. Okay, so now this is where it gets interesting. So here we have 3, which we know to be 1. So what we would do is say, okay, so my distance, my max distance is 9, index 9. So we would binary search it and say, hey, 9 reaches 7, and 7 takes 0 jumps. So like 9, the goalpost closest to the left of this index is index 7, which is 0 jumps. So that means you must be 1 jump. 0, so it's the number on the goalpost plus 1. And then we store the original, which is 6. So this says, now the leftmost index to achieve the solution with 1 jump is index 6. Okay, and now I goes here. So this says, okay, so our potential is index 11. So we would binary search here and find 48 minutes. Okay, so we would find that the closest goalpost to the left of me is goalpost 0 at index 7. So it would take me 1 jump. So now I'll update whatever 1 jump was before. So I am the new goalpost now. Index 5 is the new goalpost now. And then I will do brown. Okay. Okay, so now this one comes along, same thing, 10. So we binary search 10, and then we see the leftmost goalpost is the 0 goalpost, which means that this can achieve 1. And since 4 is less than 5, that will always be true because of the way that we're iterating backwards. So we can just update this to index 4, and our goalpost moves over. Okay, 2. So this item's max potential is 5. And when I say max potential, that's the furthest you can jump from this point. So 5. So we binary search 5, in here. And we find that index 4 is the left, it's the closest goalpost to my left, and its value is 1. So that means it will take me 2 jumps to get to the solution. And my index is 3. So now we introduce a new goalpost. Okay. And now here, my max potential, so I moves, my max potential is 4. So if I binary search 4, we find, so I think this would be the key and this would be the values probably. So you'd binary search through the key. So this will be key and value. It's a little confusing. So I'm going to switch them actually. Okay. So if we binary search 4, we see, okay, 4 is in here and it's, 4 is the 1 goalpost. So I can reach 1. So that means I'm 2. So if I'm 2, then we would have to update this number. So we can update this number. My question is, how could we, do you need like 2? Because here would help us out on how to update the actual number. Maybe we need 2 different ones, but for now, I'm just going to say, okay, so now 4 would replace, no, not 4, 2 would replace 2, because that's the index. These would change. Okay, so then that would go here. And now, I goes here, so our max jump length at this point is 6. We binary search 6 and we find that 4 is the next smallest. So that means I can achieve the solution in 2 jumps. Let me undo that. So I can achieve the solution of 2 jumps and my index is 1. So this is the new 2 goalpost. Okay, and now let's look at something like 10. So 10 here, 10 plus 0, my max jump length is to position 10. So I binary search that and I see, oh, it's 0. Yeah, this actually would work for sure. The only problem is updating the minimum. I feel you would need something that maps. So this is, you have to binary search this, but you need to update it as well. All right, so let's, so this would be n log n. Because for each element, you have to do a binary search. So I could do it in n log n. The only problem is the dictionary, right? So at every point, you have to binary search through the indices of the goalposts. And then get the number of jumps. And then if necessary, yeah, so, okay, so you binary search through indices of goalposts. And when I say goalposts, that's just like the cutoff. So everything in here, if you can reach any of these positions, you can solve it in 1 jump. If you can reach any of these positions, you can solve it in 2 jumps. Only because if you can reach this, it means you can also reach this, which, you would just take this one. So that's how I'm looking at it. Okay, so you binary search through the goalposts, and Then what you do is update the index at that goalpost. And then our solution is what? What's our solution? It's whatever we can get at index 0. So solution is the result of binary search at index 0. All right, so I guess I could have leftmost goal index 2 jumps and jumps to leftmost goal index. All right, so we'll iterate through it backwards. So for I in, how much time? 56. All right, for I in range, length of nums minus 2, -1, -1. We want to, yeah, okay, so what we want to do is start here and we want to binary search. So maybe I could make binary search, which takes in a target and the left bound and the right bound. So we'll say yeah, all right, so we'll say middle equals R minus L, and then while I guess num, are we doing nums? No, we're not. We're binary searching through this, so I'll just take a list as a parameter. Okay, so while a list of M doesn't equal target, we'll say while, no, we don't do that. We say while L is less than R, if a list of M equals to, and then this would go in here. This is wrong. We have to find the midpoint of L and R, which I will update. Okay, so if it equals target, then we should return M as the index. So this will return index. So when we binary search through these, we want to find the next left element in our array. So we're going to take, so let's say we take a list 174. Yeah, so this is why basics is good, is because I need to know exactly what I'm binary searching through. So okay, so let's just copy this example. So I'm going to do it again in more depth. I'm not just going to, I'm going to code while I do it this time. 0, 1, 2, 3, 4, 5, 6, 7. Okay. So 0 takes and this. So index 7 is the goalpost for 0 jumps. All right. So then here we're going to binary search 3 in 7. Or 9. It would be 9. So we're going to search for 9. And I don't even know what L and R would be. I guess L and R would be 0. So in this case, if we exit without finding it, we would just return L, I guess. Okay, this is a bit of a weird case, so I'm going to skip it and then come back to it. So 6 is the goalpost for 1, and then 5. So I'm just going to go to like a general case just to help me understand, and then I'll make sure it works for the edge cases. Okay, so when we get to here, so our maximum potential is 10, and our list is 5 and 7. So here L is left than R. So mid equals isn't it R minus L like that? So that would be 1 minus 0 divided by 2, so 0. So mid equals 5. If a list of mid is less than, so if this number that we're checking is less than target, then we want to search the right half. So L would equal R plus 1. I guess, yeah, I'm just going to write it out. List of M is greater than target. So the one that we search is greater than target, so we want to search the right half. Like that. So I'm pretty sure that's binary search. Okay, so in this case, 5 is less than 10, so we want to search this half, so L will become here. And then that would mean that L is greater than R, but what if it was 7? If it was 7. Okay, so let me just focus on writing binary search for a second. So let's say binary search of 5, 7, and our target will be 7. And let's just say L equals 0, not muted, and R equals the list of -1. No, length of a list minus 1. Failed to compile. Okay, let's compile. Requires L and R. It does. Yeah, we're going pretty over time. All right. So we didn't find 7. Yeah, so I think it has to do with this. So what do we want to happen? Well, maybe we could set... Well, normally, let's say we have, let's say like 1, 3, 4, 5, 7, 8, and we're searching for 6. So 0, 1, 2, 3, 4, 5. So with binary search, L starts here and R starts here. And then the midpoint is R minus L, integer division 2. So it would be 5 minus 0, integer division 2, so that would be 2. So mid would be here. So 6 is greater than that, so L should move where? Right now I have it so it should move here, which would make sense because we know that none of this is it. Okay, and now what? Is this not right? Oh, M plus 1. Okay. Like that. Still not found. M plus 1. So what about if you have 2? So M is here, and then L would go to M plus 1. Yeah, that looks right. And then if they're equal to each other, then that's also fine. It's not? Okay. But what if you try to binary search? Don't you need that? Because what if you want to binary search like this with just one element, then L and R would be here. Maybe you just return L instead. Let me just try another example. 1, 0. But what if it's not in there? You can't just return L. Yeah, so I need to review binary search apparently, but so if you're searching for 7, so if you're searching for an element in a 1 elements list in binary search, then you have to, it has to be while L is less than or equal to R, because you need to search it, because you have to say, is it equal to target? Is this part wrong? Is it R plus L? No, it shouldn't be. This R minus L integer division 2 seems to be working. So let me see, why does this give me an infinite loop? It doesn't? It does. Yeah, it's been 1 hour and 6 minutes. So I think what I have to do is I'll probably review my binary search and then try coding the solution on my own time. Okay, so it's at 1, 1. So m equals 0. So why is it not going out of bounds? So if we have 0, 0, then m should be 0 minus 0 integer division 2, which is 0. It doesn't equal the target. It's either less than or greater than. So in this case, the target is greater than 1. So R goes to -1. Oh. Wait, not O. Because R is now -1. Why is R... Okay, let me print M. M is 0. Do I have this part wrong? If it's less, I might have this part wrong. So if what we're looking, no, so if what we found is less than the target, so if we found 6 in the middle, but we're looking for 7, then we want to search the right half. Is this incorrect? Let me see which case it's taking. I mean, it should be taking 2 because 1, oh. Could I have it wrong? Because this is not actually happening. So it's taking case 1. So 1 is less than 7. That makes sense. So because 1 is less than 7, so in this case, 4 is less than 6. So we should search the right half. So L should go up. Is this wrong? I don't know what. Yeah, sorry guys. This is unfortunate. I think I'll just probably do the rest of this on my own. And so either way, I got the so yeah, let's just recap. So I got the n squared solution. I submitted it on LeetCode and it looked like other people were doing it faster. So I'm pretty sure I have an n log n solution based on like the whiteboarding that I was doing. Now I'm just struggling with binary search. So, that's why it's good to have the basics and just keep doing them. So this is good that I ran into this problem because that's what practice is for. Yeah, I did go through the binary search section, but that's why it's good to kind of review stuff and go back through it because I guess I forgot how to write a basic binary search. So yeah, thank you guys for watching. Today was day 46, and I will see everybody tomorrow for day 47.